Hi everybody. So I'm from the High Performance Computing Center in Stuttgart, so today I will talk about generally benchmarking quantum algorithms, and half of it's going to be quantum and half classical. So this is the first problem. So benchmarking quantum computers today, and then I'll be essentially doing classical emulation of this problem and kind of making the two compete. And these are some motivations for it, written below. So for benchmarking the quantum problem, I use volumetric benchmarking, if you've heard of this. So on this slide, I just like this example. So it's just a nice kind of back of the envelope calculation for quantum errors. So if you imagine taking the bit flip operator and very simple quantum circuit, just one qubit, and you keep applying the bit flip operator d times, then if you have no gate error, then you can imagine it on the block sphere. Then you just keep flipping between the two, and you get this perfect result going between -1 and 1. But a rough value for the gate error is about 3% experimentally. And so when you plot the analytical result, after just 25, after just a gate of 25, you get a completely different result. So I use this benchmarking suite here. It's quite a nice one. It's from quite a large consortium of people that met together and agreed on a suite. And this is the main ideas from their suite. So you take a given algorithm, and then you systematically increase the size of that algorithm. So the number of qubits, the width, and the depth. And then you just make it bigger and bigger and bigger, and you measure the fidelity of the result and see how good it is. So they have lots of different algorithms implemented. So the number of qubits is like an obvious parameter. What's not so obvious, and what some people might find strange, is how the depth is measured. So you can measure it 3 ways. Algorithmic depth, which is what you might be used to. Actually, the depth in the basis of the algorithm. You can measure the actual depth on the device, like the actual number of physical gates on the device that it takes after you did all the compiling and stuff. And you could also just go to a normalized basis, and they choose the normalized basis, and it's basically because it's easier to compare between different algorithms. So I have an example from another paper for this. So they take exactly the same algorithm, and then they take the quantum volume circuits, and they say, we're going to compile this circuit to loads and loads of different backends. So they compile it onto superconducting devices, onto ion trap devices. They use loads of different compilation techniques, and the key take home is the depths that you get are really, really different, and so then it's going to take different times, and classically you would think the time is quite important. But you can't even compare the time here. So these are the results from using this benchmarking suite. So the creation times and the execution times are really quite small. They're under a second. So we're going from 4 to 6 to 8 qubits, and this is for the VQE algorithm. So here's the different depths. For 8 qubits, you got, I think it's a depth of like 26. And then if you take the depths in a normalized basis, where everything can be compiled to this basis, then it's much larger. It's over 1,500. And this figure on the right is just walking through this volumetric space and then measuring the fidelity, how good the result is. And so 4 qubits is good, 6 qubits is getting bad, and then 8 qubits, about a depth of 26, is already terrible. So the key limiting factor is the error rates. They're simply too high at the moment to do things, useful things. Although one caveat, there is no error mitigation here, so maybe you could make it a bit better. So now we completely switch ideas, and this is can I beat the can I throw a GPU at this problem and emulate the full state vector classically? So I used the NVIDIA benchmarking suite for this. And this is kind of an overview of the different methods. So you would write your code. Then let's just take, so Qiskit could be the front end. And then you could actually put it on a real device, or a lot of people put it on a simulator. And then the things like QQuantum are accelerator libraries for simulators. And they basically are optimized to do the mathematical operations really, really fast. So an analog would be machine learning libraries like PyTorch and TensorFlow, and then they have they themselves rely on accelerator libraries like QDNN. So this is like the quickest explanation of what's going on one slide. So we want to emulate the entire Hilbert space. We're taking the entire state vector, all the amplitudes, and we have to stick that in classical memory. Then we have to do lots of matrix operations for the gates, and then sample at the end. So you can't even store its state vector on one device because it's enormous. So if you get towards around 30 qubits, it's already getting to around 40 gigabytes. So it's really big and hard to store. So you have to split the state vector up into chunks. And there's also various techniques to take circuits and also split them into chunks. So this is one approach to doing that. So these are the results. So this on the left is one GPU, and you're increasing the number of qubits and then simply measuring the execution time. So we've got, this is CPU time, and the scale is logarithmic. So this CPU time is much worse than the GPU times here. And this difference is around 10x. So you get a 10x speed up by using a GPU. And then if you try to do 33 qubits, then you'll get a CUDA out of memory error because the state vector is too big. So this is what happens when this is a weak scaling. So the idea is to keep the problem size per processor the same. And you just have to, because the state vector is doubling every time, then you have to keep doubling the amount of GPUs. So one GPU, two GPUs, four GPUs, and then 8. And well, it still has a very low execution time. The limiting thing is the memory. It's memory bound. So 32 qubits is like 40 gigabytes. So multiply that by 8. That's a lot of memory. So it scales quite badly. So we've got the quantum results that are suffering a lot from the errors on the devices, and then classical emulation that I would say a rough limit that people give is about 50 qubits, and it's just unreasonable to really try to simulate any more than this on a classical computer. Thank you for your attention, and do you have any questions? Okay, I will be around the talk area if anybody has stupid questions that they didn't want to ask. Thank you.